Okay, so how's everybody making out today? Good. Anybody have any questions for me before we begin? No. All right. So what I want to talk about today is a couple of very useful tools that are they're available in Python, but they're available in usually most major programming languages have some version of these things in their standard libraries. And these are things that in Python are called sets and dictionaries. So the easier one of these to define is a set. And that term comes from mathematics. And is there anybody who can tell me in mathematics, what is a set? Yeah. Okay, so it's a group or a collection of, you said, unique. Usually we say distinct. So it's a collection of distinct objects. And is there another sort of defining feature of sets that's usually included in the definition? Yeah. Yeah, so it's not in the definition of a set, but there are standard sort of operations we perform on sets, taking their union, taking their difference or their symmetric difference. But a set itself, it's a collection of things, usually called the elements of the set. And they're distinct, meaning that you can't have the same thing in there twice. And there's another sort of feature that's often used. Yep. But that's an example of a set, the empty set. But the word I'm looking for or the notion I'm looking for is it's unordered. So formally the mathematical definition is an unordered collection of distinct items or distinct elements. Okay? So let's see what those things mean. So in Python you can make a set just by doing this. So now S is a set. If I try and inspect S, it tells me that it's a set. That's how I can make it again. And I can add things to a set or remove things from the set. So for example, I can say add 4. And now if I look at S, it shows me S as using this sort of notation that if you've studied set theory before, is familiar, curly braces, and there's one element in there, and it's the value 4. And if I do something like s.add 7, and I look at S, I see 4 and 7. Let's add something else. Let's say, and now I see S contains 3 elements, the integer 4, the string Patrick, and the integer 7. And here you see one aspect, which is this unordered aspect. So when I look in the set, I mean, if it's going to show me the things that are in there, it has to show them to me in some order. There's no way around that. But it's not in any order that really makes any kind of sense, right? It's not the order in which I added the things, because I added 4, and then I added 7, and then I added this string Patrick. It's not in any order that you would think of sorting these 3 things, because 4 and 7 are integers. Why would the string Patrick go in between 4 and 7 in any kind of sorted order? So that doesn't make sense. So when we say that a set is an unordered collection, we mean that you put things in it, they go in, they happen to be there, or they happen to come out in some order, but it's not dependable, and it's not something that you can use to help you in any way. They just happen to be there. If you ask for the elements of a set, then you get them in some order, but don't rely on that particular order. You'll get each of the elements exactly once, but you don't know what order necessarily. Now for the uniqueness, I can say something like s.add 7, and that doesn't crash or anything, but if I look in my set, I see that it hasn't changed at all because I tried to add a particular value twice. Okay. And if I try and add Patrick again, can't add that up. Okay, so you can add things, you can remove things, you can iterate over the elements of a set. So you can say, just like you can iterate over the elements of a list, you can say for x in S, maybe something like print x, and that will print, x will take on each of the values in the set, Steve, 4, Patrick, and 7, and it'll execute that block of code that I provided, which is just this print statement that says to print whatever x is. Okay. So that's all fine and dandy. So we can think then about what kinds of things sets are good for. But the really interesting thing about sets and the really useful thing about sets is we can ask if things are in sets or not. And what makes sets so useful for this is they're very fast at answering that question. Okay. So you won't see it here in a set of size 4. You can't really see it. But for example, I can say, is 4 in S? That's true. Is 5 in S? That's false, right? Because S contains Steve, 4, Patrick, and 7. And S, the set, can be enormous. It can have millions and millions of elements, and yet I can still ask very quickly whether or not something is in the set S. So it'll, in fact, the time that it takes to determine if a particular value is in the set S or not is actually independent of the size of S. So it doesn't matter if it has 1 million elements, it doesn't matter if it has 2 million elements, it doesn't matter if it has 1 billion elements or if it has 10 elements. Querying asking any of those questions takes about the same amount of time for any of those sizes. Okay. All right, so let's try and do something useful with sets. So let's, words is open, user share dict words, and I think it was enough to split that one. So remember on my system, and you can download the same file, there's this dictionary used for spell checking, and it's in this file called words in some particular directory, user share dict. So I'll open it, and I'll read it, and then I'll split it up into its individual words. So let's make sure I got that right. So the first 50 values in there are all these words that start with A. How many words are in there? There's about 102,000 of them. And let's say in, I don't know, if I look at 75,000 up to 75,050, I see a bunch of words that start with P. Okay, so a good collection of words. All right. So let's do something simple. Let's turn those into a set. So right now, words is a list of things. They're all in this particular order. So let's turn them into a set. We'll call it word set. And you can do that by just calling the set function on this list of words. And what you get back is a set of words. Okay. It also has 102,305 elements in it. So what can we deduce about that then? From the fact that the list and the set have the same size? Yeah? Yeah. So in the original list of words, there were no duplicates, because otherwise the set would have gotten rid of them. If the same word appeared twice, then the set would have not put it in more than once. Okay. How about if well, why not? Let's have a look at that word set. It's going to be big. There it is. Notice anything different than, let's say, the word list? Yeah. Yeah. I mean, it's ordered, but not in any order that I recognize. It's ordered because it has to be. I mean, when you want to look at things, they have to be printed in some order, but I don't know what that order is. It's unrecognizable and not particularly useful to me. Can I ask if something is in there? So that says true. Words. I can also ask if it's in words, and that also says true, so good. It gives the same answer in both cases. And you can't see it here, but one of those is very fast, and the other one also appears very fast, but that's just because to us, the difference between a tenth of a second and a millisecond is kind of not even distinguishable, at least when we're looking at this. So we'll have to, if we want to see the difference, we'll have to try this out. So I think on one of the tutorials, you may have been asked this question of opening up this Word file and finding the anonyms. Does anybody remember what an anonym was? In fact, we did this already in like one of the first classes. So an anonym is a word that if you reverse it, you get a word. Not necessarily the same word, but you get a word. So palindromes are words that if you reverse them, you get the same word again. But anonyms are, so every palindrome is an anonym because you take a palindrome, you reverse it. I mean, if the original thing was a word, then the new thing is a word. But an anonym, you may get a different word, but it is at least a word. Okay? So what if we want to look at all of the anonyms in this dictionary? This is like most of English here. So how can we do that? So first let's see. Let's do this. Can we ask if these two things are equal? D-A-E. Okay, so those won't be equal because the reverse thing is that. Does anybody remember how we reverse strings? No? Oh, I remember. It's a one-liner. We use this fancy indexing. We ask for the whole string, starting from I don't care, the beginning or someplace, and going to all the way to the end, but counting by -1, so counting backwards. So that'll give us this thing reversed. So we've got this word set, and I'm interested in the anonyms. So the things that if I reverse them, then they are themselves a word. So let's say I'm interested in the words W for W in the word set, but only if W is equal to W reversed. Okay. So there are all the antonyms in that dictionary. It's not a huge list. Certainly all of the palindromes are in there. Oh, no, those are not the antonyms. Those are the palindromes, rather. So how would I get the antonyms? So this is palindromes. The word is equal to itself reversed. If I want antonyms, yes? So if W reversed is in the word set. So that's a considerably longer list. Not huge, but still longer. And you see it includes palindromes, but it also includes things like do, which is wed backwards, loud, which is dual, and things like this. Speed, which is deeps, and so on. Okay, so that's good. And that was fast, right? I mean, here's from the time I press enter till I get this thing, it's pretty much instant. And that's kind of impressive because this is going through all the words in my word set. There's about 102,000 of them. And for each one, it's reversing it. That doesn't take long because the words are short. But then it's looking in the entire word set again to see if that reverse thing is in the set. So if you want to see, is that, so that's how fast it is. Pretty much instantaneous. But we can compare that to getting the same result by, instead of looking in the word set, we can look at the list of words that we have. We still have that flying around. And that's how long it takes. So I think we saw that this will finish in maybe a minute or two, but that's quite a difference, right? So the thing to take home from this discussion about sets is that the thing that they're really good at, I mean, it's nice. They remove duplicates if that's something you're into. But the thing that they're really good at is checking if things are in there. So this is still plugging away, right? And why is that happening? Well, we have 102,000 words. For each one, we reverse it. And then we have to look through that list of 102,000 words to see if that reverse thing is in that list. Versus a set, which somehow manages to figure out if it's in there without looking through all of them. Okay. So I hope that that's an impressive demonstration of why it's important to choose your data structure wisely. And in this case, right, it's the difference between something that takes no time at all and something that's still going. In fact, I'm tired of watching it, so I'm just going to stop it. And in fact, if you weren't really confident in what you were doing, you might have think that there was something incorrect with your code, that you had written some kind of infinite loop or something because it was taking that long to execute. It never seemed to end. But in fact, that will eventually end. It'll just take a long time to get there. Yeah. Why is it much faster in a set? Well, because a set organizes its elements in a very specific or special way using what's called a hash function, so that it can, it puts them in a list, but it puts them in a list in such a way that if I look at some value, I will know just by looking at that one value where it should be in the list. And so then the set goes and it looks in the list at that location, and maybe it finds the thing there, in which case it says, yeah, I'm in the set. Or it looks in the list in that location and the thing that it was looking for is not there, in which case it says, yeah, this thing is not in the set. So basically a set, it stores these things ultimately as a list, but not in the order that they came in, or not in the order that's some sorted thing, but it's in some way that it can magically assign for everything that it sees a location where it should be in that list if it's going to be in the list at all. So a set ends up looking in one, maybe a couple of list locations to determine if something is there or not, whereas in the list, in this case, you have to look at 102,000 locations to determine that something is not in the list. And that's sort of why the order, when we say a set is unordered, actually internally it is ordered, but it's in a way that it's ordered to make it very fast to do those lookups. But for us, that appears to be some kind of random order. We can't do anything useful with that order externally. So it doesn't, you give up any notion of ordering. What you gain is very, very fast tests, membership tests, if something is in the set. Okay? All right. Is that clear? Good. Okay. So I said I would talk about two data structures. One of them is sets. Maybe we'll use those a couple times more. Another one is dictionaries, and these two things are very closely related. So a dictionary in Python and in a lot of other languages is a thing that allows you to take a set of what we call keys. So there's this set of keys, and for each key you can assign it a value. So a dictionary stores a mapping from keys onto values. And the keys have to form a set. So for any key that is in my dictionary, there's exactly one of them, and it maps to some particular value. The values don't have to form a set. For example, there could be a whole bunch of different keys that map to the same value. So let's do this by example. So we'll say that D is equal to a dictionary. That's how you make one of these in Python. We look at it. It looks to us like an empty set. And in fact, there's a good reason for that. It's that internally, dictionaries and sets are implemented in a pretty much the same way. And dictionaries, the syntax for them is very much like arrays, or lists. So in lists, you can say things like the list at position I, what is the value at that thing? In dictionaries, you say at this key, what is the value? Or you can set the value at this key. So I can say, for example, D at 3 or D at 4 is equal to Patrick. If I look at this thing, it tells me my dictionary contains one entry, and it's the mapping from 4 onto Patrick. And if I say, what is D at 4? It's Patrick. Okay? But I can also, the keys don't have to be integers, so I can say D at Fred equals maybe a student number. So what's in my dictionary now? There's two mappings, from 4 to Patrick and from Fred to maybe Fred's student number. If I look at this thing, what's stored at that position? It's Fred's student number. Okay? And it kind of makes sense then when I say that the keys have to form a set, because otherwise if you had two keys that were the same, what would it mean then to ask for the value at that key? Right? Because, well, if those two keys have different, are both in this, two copies of the same key exist, well, then they might point to different values, and it wouldn't even make sense to ask what value does that key refer to. Okay? All right. So we can use these dictionaries, and in some ways they're a lot like lists, because lists sort of map integers onto values, like the integers 0, 1, 2, 3 onto values. But they're also quite different because the keys, the things you can index with, they can be anything: strings, integers, floats. Though I don't recommend it. Any of those things are an option. So let's see what we can do with a dictionary. So we've still got our word list, right? We haven't changed things. So we've still got this big list of words that we loaded. Now, does anybody know what an anagram is? Or what anagrams are, or a pair of anagrams? Yeah?
It's a word that has the same letters as another word.
Yeah. So, two words are anagrams of each other if they, you can rearrange them so that you can take the letters of one word and rearrange it so that you get the other word. Okay? So, and that means that, if I have three words, A, B, and C, and A and B are anagrams, and B and C are anagrams, then A and C are also anagrams because I can rearrange the letters of A to make B, and I can rearrange the letters of B to make C. So this anagram relationship is what's called transitive, and it's also symmetric, right? If I take any word, it's an anagram of itself. I just don't have to rearrange the letters even. And so that means this anagram relationship, it defines something called a set of equivalence classes, which means we can take all of our words and partition them into sets where for any one of those sets, one of those groups, then all of the words used in that particular group use the same letters. So let's try and do that and see what we find and what we can do with this. So if we want to partition into, let's write this as a function, otherwise we'll lose too much. Okay, so we open user share dict words, we read it, we split it into lines, or just split. Okay, and so what do we want to do? We want to say for W in words, we're going to make a dictionary called anagrams. And it's going to be one of these maps from something onto lists of words. Okay? So what we want is that all of the words in a group share, the same, actually, multi-set of letters. So let's think about how we can do that. In particular, let's write a little function which is, we'll call it canonical. So it takes a word, convert the string W into its canonical form. And the way we're going to do that, we've seen also this trick before. We're going to take W and sort its letters. So for example, if W equals head, then sorted of W is a list containing each of the letters in W in sorted order. And I'd like to keep things looking pretty, so let's make this into a single string. So that means we'll take all of those letters and join them back together with no spaces in between them. Okay. So for the word head, its canonical form is ADEH. And the point here is that if two words are anagrams, that means the letters used in this word are the same as the letters used in this other word, well then they're both going to have the same canonical form, right? If I take the letters in this word and I sort them, and I take the letters in this word and I sort them, then I'm going to get the same thing in both cases. Okay? So, to convert to canonical form, we'll just return the sorted thing, but we'd like a string, so let's join all those letters that we get in the sorted list of letters. We'll join them with no spaces in between. Okay. All right. And let's look again at our dictionary and see what kind of operations it supports. So what can I ask from dictionaries? Well, I can ask, for example, is 4 in my dictionary? The answer is false. Is 6 in my dictionary? The answer is true. And what if I ask if help is in my dictionary? So that says it's false. And the reason is, for a dictionary, when I ask if something is in the dictionary, it really means, is that key in the dictionary, not is that value in the dictionary. And if you think about this for a minute, you'll realize, yeah, that kind of makes sense, because dictionaries are organized so that you can access things by their key, and so it's fast to do that, whereas if you tried to check if a value is in a dictionary, it's kind of like the same problem you have with checking if something is in a list. You just have to look through all the values to see if it's there. That's discouraged, so there's a function somewhere in Python to do that, but it has a strange name, it's hard to type, and that's because they don't want you using it, because it's not efficient. Okay? So here's what we're going to do. All right, for every word in my list of words, first thing I should do is convert it into a canonical form. So let's call that C is canonical form of W. And I'm keeping this list of, this dictionary of anagrams, where the keys are supposed to be the canonical forms and the elements are lists. So first thing we want to know is, we see this new word, we sort it to get its canonical form, and we'd like to know, have we ever seen this thing before? So have we ever seen a word like this before? So we can say, if C is in my dictionary of anagrams, then I should do something. Well, if C is in there, that means I'm allowed to look up the value there. And that value is actually, I'm going to make it so that that value is a list. And I'm going to add the word W to that list. So here is another word that has the same canonical form as some list of words that I've already found. Otherwise, this is the first time that I have seen this canonical form before. So I've never seen a word that's an anagram with the current word W. So I do something like anagrams at C is equal to a list. And that list contains just, well, actually I don't even have to do that. It's a list that just contains W. Okay. All right. So let's give this a test. List object has no member add. It's not add, it's append. Unfortunately, I'm teaching simultaneously a data structures course, a second-year data structures course, which is in Java. And Java has all these same notions, lists and things as Python, and unfortunately all the things have different names. So in Java, when you want to add something to a list, you say add. In Python, you say append. So I'll make these kinds of mistakes frequently. let's say. So bear with me. All right, so that seemed to load, and this code executed. So I should now have a dictionary of anagrams. Okay, so there's this dictionary of anagrams. It has length 96,844. So that was generated from a list of words that had 102,000 words. Now, does it make sense that this dictionary is shorter? Yes, it does, because this dictionary has glommed together all the words that are, using the same letters. So let's say in this dictionary, anagrams. So give me a word. Any word. Any non-trivial word. 4 letters or more. Really? Just pick a word. What? Computer. So there's exactly one word in the dictionary which is an anagram of computer, and it's the word computer. We can try anything now. Apple doesn't help. What about eat? So eat has several anagrams. Ate, eat, eta, and tea. So if we look at this dictionary, and it's going to be enormous, but it looks like this. It's split up into these keys, right? So here's a key, ipse, which is a single thing. And actually most of them, nothing exciting happens, right? You get one, basically one thing leads you to, or one key leads you to one word. So we saw that with computer and so on. But, there's something in here, so it's not that easy to see it. So let's try and inspect this a little more carefully. And this is often a problem in working with data, is you do something and you compute something and you don't even know how to look at the result. It's so big. But let's try and look at this a little more carefully. So I have this big dictionary of anagrams. Let's take it to a list, convert it to a list. No, just even more carefully still. For every canonical form in anagrams, AL is equal to a list. For every canonical form in anagrams, here's what we'll do. We will say AL dot append a pair of things, the canonical form and the list of words associated with it. Okay, so now we've got this big list, AL. If we look at AL at 0, it's the word A, whose list of anagrams is just one thing. If I look at AL at 500, we can kind of randomly sample this thing. In fact, we can import random and do something like random.choice AL, freewheel, hangouts, unhinging, rennet, demasking, horsemanship. So most words, or at least most canonical forms, are not anagrams. Okay. On the other hand, we have some things that are seriously in large sets, like tea, for example. It's a 3-letter word that has four 4 different anagrams in its set. So maybe we'd want to look at the interesting data, which is the words which are really involved in a lot of anagrams, or sort of the large classes of these things. So let's try and do this another way. So let's we'll call this the anagram counter. It's another way of putting these things in a list. And what we'll do is we'll store a pair, which is the number of anagrams for that particular canonical form. Okay? And maybe so that we're not looking at canonical forms, we'll actually look at one of the elements in this. The first element of that list. Okay, so let's see, AC up to 50, or AL up to 50. Let me just fix that. Okay, so we see lots of things that occur once, and there they are. But we can sort this thing now. So if we sort AC, and we look at the end of it, now we see some interesting things. So OPTS, OPTS, has 6 anagrams. What are they? We can ask that by looking at POTS, spot, stop, tops. Persist has 5 anagrams. Persist, priests, spriest, sprites, and stripes. Okay. So really powerful way to store these things. And if you like to play word games, then this is a useful way to do this. And it's just a few lines of Python code. All right. Okay. So this is like fun stuff to play with. But what if you want to do something useful? Well, what I've seen here, I've happened to have already downloaded a couple of files. One of them is called this NASDAQ listed.txt, and let's look at the first 10 lines of it. So it's a list of companies, publicly traded companies, that it's in a CSV format. And if we look at it, we'll realize, yeah, it looks like there's one sort of line per company. And what I see here is 4-letter symbol. On stock markets, that's typically there's a 4-letter symbol for the company that you're interested in, and then the full name of the company, and then some other information that maybe means something to somebody who's interested in stock markets. Okay? And those things are separated by a vertical bar. Okay? So let's open that up and do something with it. So let's do the following with open NASDAQ listed.txt as CSV file. Since it's a CSV file, we might as well use the CSV library, although we could do it in fewer lines of code, but I would like you to remember about the existence of this library. Reader is csv.reader, CSV file. And what were the things I need? delimiter equal to vertical bar. I think that's the only important thing here. I don't think anything is quoted in this file, so we don't need to worry about what character is used for quotes. And then say so what we would like is to maybe make a dictionary that takes us from these symbols, these four-letter symbols, onto the actual name of the company. Okay. So for that, we'll make a dictionary. We'll call that symbol to name. And then we say for row and reader. So now for each row in this file, each line in this file, we now have a row, which is just a list. The first element of that list should be the symbol, and the second element of that list should be the name of the company. So we take our dictionary and let's do this. Maybe we can do it slowly. Symbol is row at 0. Name is row at 1. And so then we'll say in our dictionary what we want is at that symbol, we should store that name. Let's see if that works. All right, so I have something here called sim to name. It has 2,734 entries, and let's see if we can look something up. We have to look up strings. So AAPL stands for Apple. Anybody else know a NASDAQ symbol? Nobody has a ton of money that they invest in stock markets? Me neither. So all we can do is check it. Okay. And so if I try and look in a dictionary for something that's not there, I guessed maybe there was a symbol called plot. It's not there, I get a key error. Okay. So if you're going to write code around this, then maybe you should check that first. So let's just quickly write some code around that and say something like input or query is equal to input, enter a NASDAQ symbol, blank to quit, and while query is not empty, something like if query is in sim to name, print the symbol, and then print the name. And otherwise, we've checked and it's not actually in the dictionary, so we don't want to look there because that'll throw an exception. So we'll say that symbol was not found. Okay, so we'll see if we've made a functioning application. Nope, there's a syntax error because I did the mistake I always make. Forgot to close the parenthesis. Okay, NASDAQ symbol, APL. There's a problem. Anybody see the mistake? So I asked for a query, and as long as the query is not the empty string, I look it up and I print it, and then I continue. What should I have done instead? Yeah. not break. What I intended to happen is I show you the result, and then you get to ask again another question, right? And so what I forgot to do was, once you've seen the result or seen that the result isn't in there at all, I should ask you the question again, which gives you a chance to enter a blank line or ask another question. Okay, NASDAQ symbol, blank to quit. So that one's not found. That's interesting. Oh, that's why. So a few lines of code and a free NASDAQ database. You can make an application that might be useful to somebody who's interested in these things. Somebody who watches that stock ticker across the bottom of CNN and says, "Oh, that one looks good. I want to know more about that." They can look up the name of the company just from these symbols. Okay. All right. So that's good. Useful and easy. Not too much more we can do with this particular piece of data. So I've got another great piece of data that we can look up online. And it's my favorite example of a wonderful book. So there's a book, in fact, a whole series of books about Varney the vampire, written in the late 1800s. The thing that's wonderful about it is that these things are what's called pulp fiction, which prioritized a lot of words, a lot of length over the quality of these things. So these are long books, and it's written in the 1800s, so it's one of the few things that the big copyright companies haven't managed to hold on to copyright to for the last 150 years. So it's freely available, and it's a long piece of text. Look at all the chapters in there. Fantastic. All of this stuff. I mean, really, really lots and lots and lots. So let's dissect this thing. Let's try to do something useful with Varney the vampire. Maybe analyze it, and maybe we can even compare it to something else. So let's. Let's have a look at this thing. So the file that I just showed you was an HTML file that includes some of the original pictures, but on the Project Gutenberg site, which keeps all of these out of copyright books, you can download a text version of it. It has size, it's about 1.8 megabytes, and it's only text. If we count it, it has 1.8 million words. So this is a novel containing 1.8 million words. Oh no, that's characters. Sorry, 332,000 words. So it's a good, hefty novel. There's lots we can do to analyze it. So maybe what we'll do is open it up. Read it. And kind of the text is kind of dirty in the sense, not that it's obscene, although it probably is in parts. I've never read the whole thing. It's dirty in the sense that if you look at it, if we just take a quick look at some of the stuff in here, there's a lot of stuff that if we're trying to analyze words, it's not so great. So for example, there's a whole pile of things here that are all capitals. So they somehow, literally in the book, the thing was that these things were typeset with chapter headings in capital letters. Probably if we're going to analyze words, we don't care about that. We don't care whether things are uppercase or lowercase. So let's take the whole thing and convert it to lowercase. What else is there? Well, there's a bunch of things that, again, if we're only interested in words and studying maybe the vocabulary of this person, or maybe doing a spell check or something, then maybe what we want to do is not care about things like punctuation, right? There's periods, there are quote characters, commas, all of those things, all of these dashes. Maybe we don't really care about any of that stuff. Okay, so we want to get rid of that somehow. So let's do that. So let's replace any of these punctuations with nothing. So periods, commas. It looks like they're using double quotes. There'll be colons and semicolons. Probably won't catch anything, but we might get a reasonably clean list of our body of text now. And now we take that body of text and we'll split it on spaces. So let's see what we get from that result. So there's the first 50 words. See, there's some weird Unicode character there that didn't work out. Let's not bother too much about it because we have 330,000 of these words anyway. And this is the sort of preface to the book that talks about where this came from in the Project Gutenberg and the license that it's released under. But if we look at maybe location 50,050 up to starting from 50,000, then yeah, we're right there in the thick of the things. It's talking about German bloodsuckers and lawyers. Maybe those two things are related, I'm not sure. Circumstances. We're right in the middle of the book here. So we've done a semi-reasonable job of splitting this up into words. We may get some things that don't help us, but whatever. Okay, so what kinds of things can we do with this list of words? Well, we could ask, for example, how big is the author? So it's a long book, so we know the author could write a lot, or the authors. But we could ask how big their vocabulary is. So how many distinct words do they know? I mean, it could be very repetitive prose, right? Just using the same words over and over. How would we figure out the size of their vocabulary? Yeah. Yeah. So that's really easy. So unique words is just what we get when we take that list of words and turn it into a set. And if we ask for the length of that set, then we will know the another missing bracket. Okay, 16,190 distinct words were used in this thing. All right, and we can look at a random choice from that thing. After importing random. So we make a list of those unique words, take a few random choice. Science, holiest, poisoning, alone, you, my, some mistakes there. Insisting, whereas, failure, hostler, denial. I don't know, some reasonable things, and also you see some things that we missed when we stripped out punctuation, but that's okay. Not the end of the world. We can do a better job at stripping punctuation on another time when we learn about regular expressions. Okay. What else could we ask about this book? So we got this huge corpus of text. What are some interesting statistics we could ask? Things that sets and dictionaries might help us with. Could we spell check it? Do we have the know-how to do a spell checker on this book? Yeah, how? Yeah. We have a dictionary, so let's use it. Dictionary in the sort of non-computer science sense, we have a list of all the words in the English language, or at least something like that. So let's call that thing speller. And that's what we get when we open user share dict words. We read it and we split it. So that gives us a list, and we would like it as a set so we can check if things are in there. All right. So let's see. So now we can say for each word in the text, if that word in the text is not in my spelling dictionary, then I can write something like unrecognized word. Print it and show it to you. Now, never done this before, but I'm guessing that it's going to give us a lot of things, some of which were our mistakes for not cleaning them up, and some of which may be legitimate misspellings, but mostly there'll be things with punctuation in them. Okay, so here's what we get. Some numbers in there. Fairbanks, Malin, Gutenberg. So this is all stuff from the end text, I'm guessing. And we got tons of stuff before that if we dig back into the book. So endeavored didn't happen to make it into our dictionary, though a better spell checker would have realized that it's just changing the tense of the verb endeavor, which I'm sure is in there. Neighborhood. Why is neighborhood not there? Yeah. Yeah, I'm guessing that the dictionary on this system is using American spelling, and this is, labored probably is another example. So there you go. Basic spell checker, color, definitely. Definitely that's correct. British and Canadian spelling, but not American. So there we've made a spell checker. What else might we do? Yep. Yeah. I might be interested in knowing, for example, the frequency with which the author uses certain words, as well as maybe the most commonly used words, although we can guess some of the most commonly used ones, but maybe there's some surprises in there. So let's try. So if we want to know the frequency with which the author uses words, well, that sounds like a problem for a Python dictionary, because what we've got is for every word, we want to know how many times it was used. So for every word, we should map it to an integer counter, which tells us how many times we've seen that word. So for that, we create a dictionary that we'll call freq for frequency. And we go through each word in the book, and if W is in our frequency, so if the word we're looking at is already in this dictionary, it means we've seen it before, and that means it's stored there with its counter. So I look at whatever value was there before, or the value that I want to store there is whatever value was there before, and now I've seen this word again, so I add 1 to the value that used to be there. So I've got this dictionary called freq that keys are words, and each key maps to each word, tells you how many times you've seen it so far. So if I see a word again, then I go and increment that counter. And otherwise, if I've never seen this word before, then, well, its counter should be created, it should be added to this thing, and with a counter of 1, because I've seen it exactly 1 time so far. Okay, let's check that out. All right, so we've got this thing, or what's the length of freq? 16,190, which should be the same thing as the length of unique, because the number of unique words was 16,190, and so then the number of entries in our frequency counter should be there. So let's look for something in there that is fairly common. And occurs 9,918 times in this book. What's even more common than and? The. 17,324 times. Or 954 times. That's an incredible difference between and or, though logically they're very close. What else might be a really frequently occurring word? Maybe even more than the. Yeah. Let's see how often vampire appears. 17 times. Is there maybe another spelling? Nope. Vampire with a Y occurs more frequently, 439 times. In a story about vampires, what else? What other things might be featured? Yeah, that seems like a good choice. Blood. Is this a good story? 92 times. Not bad. There's one that we saw just in our random sampling. Thought we saw bloodthirsty. Oh, like so. 4 times. Bloodthirsty. Okay. What about what? Sanguine. I think you're maybe overestimating the vocabulary of this particular authors. 4 times, as often as bloodthirsty. Any other suggestions? I don't know. What do vampires do? They kill people. 27 deaths, I would guess. Yeah. The letter A. 7,180. So compared to the, that's less than half the number of occurrences. So this author likes to be specific about things rather than general. Yeah? We can check that. So, and occurs, I don't know, that's probably a sort of a standard thing, depending on whether the thing that comes after it begins with a vowel or not. Okay. Kill, death, lots of 138 times. Murder. What about killing vampires? Steak. What other things can you do to kill vampires? Sunlight. Burn. Garlic. Garlic. Good idea. Not even once. So maybe this garlic thing is actually a feature of modern day vampires, or let's say post Bram Stoker vampires. Burn. Holy water might be, no, maybe just holy twice. It's not a very holy book. Okay, so we now have access to for any word that we're interested in. We can see how often it occurs. Now, what if I want to see the most frequently occurring ones? So that requires a little bit more work. Basically, we have all the data we need to know what are the most frequently occurring things, but we don't have it the way we need it yet, right? We have this whole set, and we know for every word how often things occur. But what we'd like to do is somehow reverse it and sort it. So let's do that. Let's make something called freak2, which will be for every word in the word set, which we could use unique. Here's what we want. We would like the number of times it occurs, and we would like the word itself. So we'll make a pair. First element of the pair is the number of times the thing occurs, and the second element of the pair is the thing itself. And we'll sort that. And are we interested in the words that occur the least frequently or the most frequently? So if I sort by this number of occurrences, what I'll get is the words that occur once, and then the words that occur twice, and so on. So I don't really want that. I want that thing reversed. So let's... All right, so let's check that out. Okay, so I can't look at the length of that thing, but maybe I can look at the first few things. 50 most occurring words in Barney the Vampire. Okay. Just convert the whole thing to a list. 50 most commonly occurring words in Barney the Vampire. Oh, no, that's the other way around. I got that backwards. 0 through 50. The, and, to, of, you, that, he, it, in, was, as, be, not, have, and so on. Okay, so nothing terribly exciting in the most frequent words. Well, what if we instead make a list of words that actually don't occur frequently at all? Maybe that'll be more interesting. So we'll take a W for W in unique. If freak at W is equal to 1. So these are the words that occur uniquely. So they might be more interesting because the author knew them and used them but chose to only use them once. So we can take a random sample of those things. Choice. Thine. That's an old word. Glimpses. Intrinsic. Displeased. Fencer. Contracts. That's not a sort of a miscontraction. Mightily, together with an exclamation point. Wine with a question mark. Novelist. Retrograde. Mine. Okay. That makes me curious how often wine occurs. 42 times. How did that compare to blood? So about half as much wine as blood in this novel. Okay, so sort of the takeaway, the moral of today's story is there are these two things, sets and dictionaries. The most important of the two are actually, the most useful of the two are actually dictionaries because they allow you to, they can do everything sets can do because the keys form a set, but they're really handy for these things where, for everything, every particular item, you have some value associated with it. So these come up in many, many applications. Think of something like even when you log in to CU Learn, what do you log in with? Well, you log in with your username or your student ID and your password. So how do you think that's implemented? Well, the student ID gets sent off to the server. The server has a dictionary that maps student IDs onto passwords so that it can check if your password was correct. And another dictionary maps student IDs onto student records, student IDs onto enrollment lists, student IDs onto whatever. So these dictionaries are really used all over the place, and you can use them too, and we will use them a lot in this course. Okay. That's it for today.